So in our final section, we're going to go through bases other than e. So what happens if I have 4 to the x? What is that derivative going to look like? And it's really just going to utilize our exponential properties. So remember, because e and the natural log function are inverses of each other, I can really write a as e to the natural log of a, as long as a is a positive number, because ultimately these two things would cancel each other out. You just land back at that input of a. So if I have the function a to the x, it's really like taking this expression, raising it to the x power, and this expression and raising it to the x power. So this would be e to the natural log of a to the x. And if I take an exponent and raise it to an exponent, you just multiply the two. So we're going to utilize this rewriting of the function a to the x and our knowledge about the derivative of e to the x to find derivatives for bases other than e. Okay? So now if on these two quantities, a to the x is e to the x natural log of a, we're going to take a derivative and apply chain rule to really see what the derivative of a to the x is. So differentiating a to the x is the same thing as differentiating e to the x times natural log of a. And for e to the x, you're going to get exactly that same function, but your chain rule tells you you've got to multiply by the derivative of the exponent. So I want to multiply by the derivative of x natural log of a. Now thinking of this expression, ln of a is just a number, natural log of 2, just a number. So ultimately this thing is just going to be a constant. So this front piece stays untouched. I have x times a constant. Derivative of 3x is 3, so the derivative of x ln of a is ln of a. Now using this rewriting, e to the x ln of a is exactly what we have up here, so I can just replace that by a to the x. So ultimately this is a to the x times the natural log of a. So in general, if you want to take the derivative with respect to x of a to the x, you get a to the x, but you have to multiply by the natural log of the base as well. So if you have a function in here, you're going to get exactly the same thing back. Then you want to times by the natural log of the base, and then because you have a function that's inside there, you've got to multiply by the derivative of that exponent. So let's get some practice. Let's differentiate 3 different functions. We're going to start nice and simple. Derivative of 7 to the x would just be 7 to the x times the natural log of the base. If you want to differentiate e to the x, following this same guideline, it's e to the x times the natural log of the base. The reason this one's so special is because this one is just 1. So that's why you end up with e to the x instead. If I want to differentiate 5 to the 1 plus 5x, we're going to get exactly the same expression back. We times it by the natural log of the base, so I get natural log of 5 attached. Because I have something other than just x, my chain rule is telling me I've got to multiply by the derivative of that exponent. So ultimately I get 5 to the 1.5x, natural log of 5, and then a 1.5 from our chain rule. Now, utilizing our information about the natural log function, we could do exactly the same thing. So we can go through the same process we did in the very first section, going through the natural log of x, but we can really also just use the change of base formula instead of having to go through implicit differentiation, because we've already seen this process. So we know the derivative of the natural log of x is 1 over x. So if I want to change that base, utilizing our change of base formula, remember to actually evaluate this in your calculator, you had to rewrite it in terms of natural log or log base 10. So we're going to take natural log of the inside, divide it by natural log of the base. And now we have no problems actually going through this derivative, because 1 over ln of a is just a constant. It's like I'm then differentiating natural log of x. So really this is 1 over the natural log of a times 1 over x. So in a similar process, the derivative of a logarithmic function with any other base is still 1 over x. You get the natural log of the base attached. Just like back up here, you get the natural log of the base attached. So same kind of process. So let's just try a couple examples before we go on to integration. We're going to start by differentiating y equals log base 4 of 6x plus 1. So utilizing this process, I still get 1 over the inside function, but now I get natural log of the base attached to it. And so I have base 4 here. Our chain rule still applies, so I've got to take the derivative of the inside. Derivative of 6x plus 1 is just 6, so I get 6 divided by the inside and natural log of the base. You can also utilize properties of your exponents before you try to take derivatives. If I want to differentiate log base 5 of the square root of x squared minus 1, that would be quite tedious because I really have 3 functions within a function. I've got my log function, I've got the square root function, and I have this polynomial. But remember, one of our properties is exponents pop out of logarithms. So the square root you can really write as x squared minus 1 to the 1/2. And then your 1/2 pops out front, and you're left with log base 5 of x squared minus 1. So now we can go ahead and utilize this to take our derivative. Y prime is going to be 1/2. Derivative of log base 5 of x squared minus 1 is 1 over the inside times the natural log of the base. Chain rule, we have to multiply by the derivative of x squared minus 1. Well, derivative of the inside is just 2x, so my bottom stays untouched. I've got 2x up top, but those 2's ultimately cancel each other out. The derivative of this will be x divided by x squared minus 1 times natural log of 5. So let's try one more example. We're going to do x cubed times this logarithmic function. And because I've got the product of 2, I've got to use product rule. So my derivative will be the first function times the derivative of the second. Then I want to differentiate x cubed, leave the logarithm alone. And then to go through the derivative of this expression, I am going to have to go through chain rule in combination with these logs. So I have something other than x on the inside. So that gives us x cubed. We get 1 over the inside function multiplied by the natural log of the base. Chain rule multiplied by the derivative of x plus 4. Derivative of x cubed is just 3x squared, so we get that times that logarithmic function. The derivative of x plus 4 is just 1, so the front piece is just x cubed divided by x plus 4, ln of 2.5, and then you keep that second piece as is. So now that we've got a bit of a hand on the differentiation, we're going to work through the integration. Luckily, we don't really have to work through the integration of these logarithmic ones of other bases because these are just treated like constants, they pop out. So you really only need to know the antiderivative of 1 over x. You don't have to worry about other bases. But for our exponential functions, absolutely, you're going to have to go through the antiderivatives of those. So ultimately, since the derivative of a to the x is a to the x natural log of a, if I want to integrate a to the x, I'm going to get a to the x back, but it's not times natural log of the base. I've got to divide by it and then add RC. This way, when I take the derivative of a to the x, I'm going to get another natural log of a that'll pop out, and these two will cancel each other out. So let's try some examples. Let's just evaluate the integral of 3 to the x dx. So we're going to get 3 to the x, but we have to divide by the natural log of the base and add c. Let's try one that's going to require a substitution. So I've got a couple different exponential pieces, but we've got this 1 plus 4 to the 3x in the bottom. So that's definitely going to be my u because it's a function within a function. So we'll let that entire denominator be u. So if I take du, the derivative of 4 to the 3x is exactly that back. You get natural log of the base, And then I've got to multiply by 3 as well because of our chain rule. Derivative of that exponent is going to be 3. Okay. So I can take care of this denominator. The 4 to the 3x dx is exactly what we have right here. So I'm missing that 3 and the natural log of 4. So we go ahead and just bring those to the other side. 1 over 3 natural log of 4 du is 4 to the 3x dx. So just rearranging this so you can see it, that's 1 over 1 plus 4 to the 3x times 4 to the 3x dx. That front piece switches over nicely to 1 over u, and this 4 to the 3x dx is exactly 1 divided by 3 natural log of 4 du. So that just pops out front of the integral. We're left with the integral of 1 over u du, which is the natural log of the absolute value of u plus c. Well, natural log of the absolute value of u switches back over to 1 plus 4 to the 3x plus c. So we've got one last example. We're going to do some more composite functions. I've got 2 to the sine x times cosine of x. Again, function within another function. So we're going to go ahead and make that inside u. So du is just cosine of x dx. So this front piece is going to switch over nicely as 2 to the u. Cosine of x dx is exactly du. So the antiderivative of this will be 1 over the natural log of 2 times 2 to the u plus c. Plugging in our value of u is 1 over natural log of 2, 2 to the sine of x plus c.